Good morning, everyone, and welcome to Day 3 of Google Cloud Next 2026. I hope you're all having a fantastic time here learning about AI and cloud technology. I certainly am having a blast, and especially because I get to meet innovators and thinkers and visionaries like all of you. And again, thank you so much for making it bright and early here this morning. Today, I'm truly humbled to share the stage with our customer, OpenAI, to learn how OpenAI uses Google Cloud infrastructure for complex multi-node inference. We have some really exciting content to share with you today, so let's get right in. A little bit about myself. I'm Ishan Sharma, Group Product Manager at Google Cloud. I lead the accelerator platform innovation for AI workloads on Google Kubernetes Engine, GKE. First, I'll speak about running AI workloads on GKE using accelerators on Google Cloud. Next, Fangyuan Li and John Fishbein, both members of technical staff at OpenAI, will dive deeper into how OpenAI is using Google Cloud's infrastructure to build massive Kubernetes GPU clusters. Let's start first with why so many organizations choose Kubernetes to run their AI workloads. In fact, Kubernetes is becoming the de facto platform for AI primarily because it allows you to orchestrate the entire AI pipeline on a single control plane. Let's dig deeper. To run massive training jobs, you need scale. GKE lets you operate at the mega scale of 130,000 nodes per cluster. For synchronous gradient operations like all reduce, you can use Q to schedule multiple nodes all at the same time concurrently and then schedule jobs with topology awareness. Finally, features like multi-tier checkpointing minimize lost progress and improve mean time to recovery. For model serving, Inference Gateway uses model server metrics to improve routing efficiency, while GPU sharing strategies like multi-instance GPU, time slicing, multi-process service, and the newly launched vGPU-based fractional machine shapes allow you to reduce your total cost of ownership. Additionally, you can scale up faster with pod snapshots, starting from a saved pod state. For agentic workloads, GK Agent Sandbox provides a secure and isolated environment for your agentic workloads, while LLMD improves utilization and time to first token latency in disaggregated serving. And KubeRay helps you run Ray servers or Ray clusters on Kubernetes. All of these workloads on a single surface, Kubernetes. Within the Kubernetes project, we at Google take pride in driving Kubernetes innovation with the largest number of contributions to the Kubernetes project every single year since its inception. Furthermore, we have re-architected the control plane of Google's managed Kubernetes offering, GKE, to handle the massive scale of AI, making GKE the Kubernetes leader in scale with support for 130,000 Kubernetes nodes per cluster. Whether you're looking to optimize for cost or drive massive performance at scale, for your AI workloads, for all your AI workloads, through GKE, you can use Google Cloud's entire GPU portfolio, including NVIDIA GPUs such as RTX Pro 6000, H100s, H200s, B200s, GB200s, GB300s, and many more. Our customers are already using the G4 VMs powered by NVIDIA's RTX Pro 6000 to serve AI models and run complex simulations on GKE. This week, we're happy to announce the general availability of fractional GPU shapes for G4 VMs, giving you 1/8, 1/4, 1/2 GPU shapes, helping you save costs when serving smaller models. Our customer 11 Labs has used G4 VMs on GKE to make their agentic text-to-speech model even faster, reducing the time to first byte by 33% down to 50 milliseconds. And if you're looking to run large-scale training and inference workloads on GKE, you can run rack-scale GPUs such as A4X VMs on GB200 NVL72, A4X Max VMs based on GB300 NVL72, and soon A5X VMs based on Vera Rubin. So let's dive deeper into how exactly you can use these powerful rack-scale systems through GKE using GB300 GPUs as an example. Now here is one host or machine instance of Google Cloud's A4X Max VMs with 4 B300 GPUs, 4 CX8 NICs, and 2 Grace CPUs. This maps to one GKE node. The next topology layer is the one NVL72 rack with 18 hosts or machine instances, each of which contains 4 GPUs for a total of 18 times 4, 72 GPUs, all connected with NVLink. This maps to one GKE node pool containing 18 GKE nodes. In Google Cloud, we refer to this topology layer as subblock. The next topology layer is a rail-aligned network block with multiple 72 GPU NVLink domains, which maps to multiple GKE node pools in GK clusters. This topology can scale out with multiple ML block rail groups mapping to more GKE node pools in one or more GKE clusters. Now, putting all of this together, we get this mapping of physical topology layers to Kubernetes concepts with a host mapping to a node, subblock to a GKE node pool, and block and networking cluster to multiple GKE node pools. On GKE, we try to make it easy for you to work with these topology layers. For example, with block and subblock targeting, you can create your GKE node pools on a specific NVLink domain rack or subblock. And to help the ease of pain of setting up GPU networking, which can be toilsome, we launched GKE Managed RDMA, which is comprised of 3 features that help you simplify and automate your VPC and subnet setup through auto networking profile, error-proof and ensure version compatibility with auto RDMA nickel, and optimize performance at scale with GKE Managed DRA Net. So let's dive deeper into these features. Setting up and configuring RDMA networking can be cumbersome and, more importantly, error-prone. With GKE Auto Networking Profiles, GKE will automatically set up and configure VPCs, subnets, IPs, RDMA NICs through just a simple flag during GKE node pool create. Now, nickel version compatibility is often a pain point where it needs to be carefully managed through the setup and also through upgrades. To help with this, we are launching GKE Automated RDMA Nickel in preview today, and this helps you get a tested version of Nickel plugin that's compatible with GKE node and kernel versions, secure pods without enabling privileged pods or host network, and safe GKE upgrades that will not break the version compatibility between RDMA user space libraries and kernel modules. So GKE Auto RDMA Nickel, this feature, can be enabled through yet another flag during GKE node pool create. And to maximize performance, DRA Net, which uses Dynamic Resource Allocation, or DRA, lets you request and allocate your high-performance network interface cards as first-class schedulable resources, similar to GPUs, compute, or memory. And with topology-aware scheduling through DRA, you can see up to 59.6% increase in bus bandwidth in all gathered tests. Now, putting all of this together, you can create a GKE node pool with GKE Auto Network Profile, GKE Auto RDMA Nickel, and GKE Managed DRA Net enabled simply through 3 simple configuration flags. You then create a resource claim template to allocate RDMA resources and include the resource claim in your pod spec. This gives you control to maximize performance simply and easily without any errors. Today, we're also launching one-click GKE clusters for AI training in preview, through which you can easily create production-ready clusters that are performance-tested, optimized for AI training. And all of this through an intuitive UI. Well, today this UI feature is available on A3 Mega, A3 Ultra and A4 VMs will continue to expand to more GPUs. Now, what's better than directly hearing from our customer, OpenAI, on how they're using Kubernetes for their workloads? How many, by show of hands, how many of you here have heard of OpenAI? I expected more. But of course, OpenAI is a household name, and it needs absolutely no introduction. I would like to invite to stage Fangyuan Li and John Fishbein, members of technical staff at OpenAI. Fangyuan focuses on RoCE, high-performance networking, and large-scale GPU clusters. And John focuses on multi-cloud GPU infrastructure, networking, and Kubernetes. Personally, it has been such an honor to get to know both of you and learn so much from you. Can't wait to hear more from you. Please come on up. Round of applause.
Thank you, Ishan. My name is Fangyuan, and this is my colleague, John. We are both engineers from the V team at OpenAI, and our team manages the Kubernetes clusters that empowers our inference workload from ChatGPT, API, and training workload that help us to build and enhance the next generation models. Today, we're going to give you a glimpse of how, at OpenAI, we manage GPU infrastructure. And more specifically, we're going to look into how we are onboarding these GPUs on GCP. All right, before we get started, let's step back a little bit and go back to the beginning of the story and see why it all happened. Around the same time last year in March, NVIDIA V1 was launched. It was a blast to the world. Many people around the world have tried it, tested, pushed it. As you can tell, the usage pattern changed almost immediately overnight. Some of you might still remember those really cute GB pictures went viral on social media, right? And we were so happy to see the world was having fun, but at the same time, as Sam called out here, GPUs were literally melting. But if we could look into the future, we would know that, NVIDIA V2 will be launched around the same time this year, but we'll be in a much, much better situation this time. If you haven't tried, give it a try, and I promise you, we won't be paged this time. But what happened? Right? The first challenge we were facing, obvious, was to acquire more GPUs. An initiative actually was started at the beginning of the year to onboard 3P or third-party GPUs onto our platform in a massive scale. We partnered up with the top providers, and Google obviously is one of the best. But still, this left us with so many unknowns. First, how do we onboard these GPUs fast enough so that capacity is still useful when the business needs it? It's all about timing. The speed of execution really matters, but at the same time, we don't want to compromise the operating model we've been already relying on. And that means specifically a set of ingress endpoints accessible directly in the existing provider. Second, our workloads, our clusters have been exclusively running on InfiniBand. Can RoCE on GCP work for us? Lastly, as new SKUs like GB200, which has NVL72, show up later this year, how can we enable NMAX cleanly and in a native way, right? And how do we manage rack-aware node lifecycle management? Okay, let's take a look at the first challenge, connectivity. Like I mentioned before, the interface we're trying to keep here is a set of ingress endpoints accessible in the existing provider. And we tend to keep that. What that means specifically is the following decision. For Kubernetes clusters, our control planes remain in the existing provider. And we're going to connect GPU nodes VM or bare metal that are sitting in a remote location into Azure's control plane. To implement it, we use the standard cloud interconnect solutions. Each cluster is a unique snowflake in its own, but at a very high level, we have ports, physical switch ports open on both ends. We establish BGP sessions, and depending on the topology of the data path, we may or may not provide providers backbone. What this really gives us is the ability to run 3 PVM as Kubernetes nodes. And in the case of bare metal nodes, we can also do IPC. OK, this is great. So now nodes are showing up in Kube, right? Let's take a look at the backend networking. Historically, our stack has this assumption that we just run on InfiniBand. And our internal libraries were actually directly built on top of libverbs. While RoCE gives us RDMA as well, it does bring Ethernet and IP networking into the picture. So to show you what I really mean concretely, let's take a quick recap at the protocols. So what you're seeing on the screen are the headers for IB, InfiniBand, and RoCE v2's protocol. And if you look at closer, what that really shows is RoCE v2 essentially replaces the IB header with an Ethernet, IP, and UDP header. And what that concretely means are the 3 things I listed here. First, just like InfiniBand, we are going to have a device under /dev, so our libraries can continue programming against it. That means when you open a QP, when you start sending data, etc., it's there. Besides this, we also have a networking device. It's just like ETH0, but with a different name. And metadata for this RoCE interface will be exposed through sysfs under sys-class InfiniBand. On the right side, what we are doing here is to list the first 4 entries for this gits table for interface metanox50. So as we know, the gits table for RoCE are actually addresses for these interfaces. And they map one-to-one to the IP addresses assigned to the interface. To give you one concrete example, let's say we have an interface called ETH111. After we assign IP 10.0.0.111 to this interface, and you should be expecting 1 entry in this git table, just looking like a bunch of zeros, then 10.0.0.111 in hex. OK, with this understanding, let's step back and take a look at our internal requirements from our workload. Our workloads, more specifically the inference workload, have been running in PaaS networking namespace for better isolation and easier policy enforcement, right? And we intend to continue doing that. Secondly, we want to minimize the number of dependencies we introduce to our runtime, both to simplify our operations in future and to minimize the risk as we were racing against the clock. Third, we actually like to share, enable this shared RoCE interface model because we do have 1 or 2 daemon sets besides the workload itself can potentially leverage RoCE to do RDMA to do its own work. OK, so how do we achieve this? The answer is pretty simple. Modus. For those who do not know, Modus is a CNI or container network interface. It not only plays very well with the existing CNI that manages the main networking interface or the front-end networking, but also can manage additional interfaces. In our case, these are the additional 4 or 8 RoCE interfaces depending on your skill. The snippet you are seeing on the left is a config from Modus. And what that achieves essentially are the 3 things. First, it's of type host device. What that means is it's going to move the host RoCE interfaces into the PaaS networking namespace. But which to move, right? PCI bus ID actually uniquely identifies those host interfaces. These IDs are constant for a given SKU. Lastly, We are using IPAM, or IP address management of type DHCP. So this is great, because that means we can leverage the existing Google infrastructure to manage IP lifecycles for workloads. To put this into context, this is actually a models config from a different provider. I won't go into details, but you can tell for the very minimal, we need to manually manage IP addresses with a patched version of models. We need to do a bunch of sysctl settings, which is kind of painful, for both. And it's very obvious how clean and simple the GCP version is. You might start wondering, right? You mentioned you want to enable this shared RoCE interface model. How can you still share it if you are moving it from the host into the specific pod's networking namespace? And you are absolutely right to challenge it, because we cannot. By moving it from host to pods, they become exclusive. And the solution for this one is IPVLAN plus IP aliasing for RDMA subnets support. This feature is still in beta. So thanks to the great collaboration with the amazing Google engineering team, we are still actively exploring and testing this out. So stay tuned. With this, I'm going to pass over to my colleague John here to talk about the rest of the challenges.
Thank you, thank you. Hi, everybody. I'm John. I'm also on the fleet team at OpenAI with Fangyuan here. Our job at a high level is onboard GPUs to OpenAI's infrastructure so that we can run ChatGPT, the API, and also training runs. So I'm going to continue with what he was talking about and continue talking about the challenges that we had to onboard GCP as an infrastructure provider for OpenAI. So yeah, jumping into it. As Fangyuan alluded to a bit earlier, one of the main challenges and problems that we were trying to address while onboarding GPUs from GCP is how do we keep the interface with our consumers the same across GPUs? People shouldn't care where their GPU is running or what cloud their GPU is running on from our perspective. It should just be a GPU is a GPU. So how do we abstract away which cloud is running on so that we can provide a unified interface for workloads to not change? So in order to do this on GCP, we needed to dive really deep into the abstractions that Google offers us to manage infrastructure. And that brings us right to MIGs, which are managed instance groups on GCP. We are extremely heavy users of MIGs. Every GCP GPU that we have in our fleet is a member of a MIG, and it makes things very easy to manage large-scale infrastructure. We can scale from one GPU node to 1,000 or many more. So I'll go into how we use that a bit. So this is an example screenshot of the MIG UI on GCP's portal. This is an example of a MIG that is currently in our fleet that is serving ChatGPT at the moment. And so what MIGs give us the ability to do is define an instance template once and then scale from that instance template a uniform fleet of many, many instances. So we at OpenAI are very, very opinionated about the software that goes into our GPU nodes. We have custom host OS images. We're very particular about the GPU drivers that we use. We want to pin stuff to specific hardware and stuff like that. So this instance template gives us the ability to express that desired state of what we want our instances to look like. And then once we have that template defined, we use MIGs to scale up those instances across many, many physical hosts and manage many instances at once. One thing about this that's really awesome is that MIGs give us the ability to plug in and manage the lifecycle of GPU nodes effectively. So Ishan alluded to this in his talk a bit, but GCP's terminology for a rack of GPUs, like a physical tower of GPUs, is a subblock, and we can actually use MIGs to target which specific physical infrastructure that I want to run on. So this is very different from traditional cloud in the fact that I don't care what physical host my infrastructure is running on. I actually just want a VM. GPU infrastructure is a bit different. You care more about the physical infrastructure that you're running on. You need to be topology aware, so to speak. And so this subblock terminology and ultimately the ML block rail group gives us the ability to control that at a much more finer grained level. But yeah, so MIGs cover most of how we provision all of our GPU instances across all of GCP and how we use that here. Next, I'm going to jump into another fun problem, which is we had to solve how do we make the latest and greatest SKU from NVIDIA of GPU, the GB200, work with GCP. And it's a very different paradigm than usual, so I'll jump into that. But before I do, I need to give some context on GPUs in general, in case you all aren't familiar. So this nice picture here shows a GB200 rack, or a set of GB200 racks. GB200 or 300 is the latest and greatest state-of-the-art SKU of GPU from NVIDIA. And it's very, very different than the previous generation. And it makes for lots of fun and interesting and challenging infrastructure problems. So the previous state-of-the-art SKU of GPU was the H200. And Ishan alluded to this a bit in his demo, but the H200 is a giant, big, beefy machine. NVIDIA took a bunch of compute, a bunch of memory, and a bunch of power and jammed it all into one big box. And it's a giant, awesome computer. And that got us really far. But applications have kept growing and growing and growing since then and have exceeded the limit that this one box can handle. And there's only so much physically that you can jam into one computer. So what did NVIDIA do? NVIDIA did what software engineers have done forever, which is instead of scaling up this one thing vertically, I'm going to scale out and scale out to many horizontally instances. So the GB200, which is what's pictured here, is not a single machine. It's sold as a rack of machines. So this tower, each tower has 18 physical hosts. Each of them have 4 GPUs in them, which form 72 GPUs altogether. And the trick here is that all of these GPUs, all of the 72 GPUs in this rack are connected via NVLink. So this forms what's called the NVL72 domain, which is any GPU in this rack can talk to any other GPU at extremely fast speeds and extremely high bandwidth. And this enables workloads to scale beyond a single node and leverage this multi-node NVLink to do more complex work. And this is required for any state-of-the-art model to run. It's just they're too big for one single machine now. So we had to figure out how to make this work on GCP, and that's a challenging problem. And the answer was a lot of things, but we used MIGs. And so the challenge is that you have to make your software systems rack aware now, not just instance aware. So one concrete example of this is IMEX. IMEX is a rack aware piece of software. And so essentially, IMEX you can think of as the control plane for NVLink across nodes. So you have to run this service on each physical host so that it makes every other host aware of the fabric that is in this slide. So all these nodes in this rack of 18 need to be aware of the other nodes that they can talk to over NVLink, this rack-aware software. And so configuring IMEX is a challenging problem that we worked very closely with the Google team to figure out a solution for. And it was challenging, but we made it work, and it's pretty awesome. If you're interested in more of the details, we have another session later today that we're going to go into more details on this. But for now, I'm going to jump back to the computer over here, and we're going to show you a really cool demo of ChatGPT running live on GCP GPUs. But yeah, let's jump into it.
All right. Can people on the back see this okay? Cool. Awesome. So what I'm going to do here is going to go through a few pods in our cluster that have and do not have RoCE and show you what that looks like firstly. Okay, let's do it. Finger crossed. Okay. All right, so firstly we're going to show you this one pod. It's a preview, I think, running in one of our clusters. Right? Next. What you're seeing here is inside this pod. This pod doesn't need RoCE at this moment. And if you check the devices, remember I mentioned there are 3 things to RoCE: a device, a networking device, and also CCFS exposed metadata. Right? So what you're seeing here are 8 devices that library can program against. And there are no networking devices in this pod because it's not requesting RoCE. The next, what I'm doing is I'm going to spin up 2 pods to check if RoCE works at the host level. They are still not requesting RoCE. But let's take a quick look at RoCE interfaces and devices on the host. So these are still the old 8 devices with a corresponding networking device named GPU, blah, blah, blah. As you can see here, there's a list of networking devices on the host. We have the standard front-end networking. We have another 8 networking interfaces with IP assigned to them. If we switch back to the Google console, you are able to see these 8 RoCE subnets created for these 8 individual interfaces. That means across all the nodes in this cluster, each interface will be put onto its corresponding RoCE subnet. And the IPAM will be managed by Google completely. So let's pick this one as an example. It has IP 10.100.135.4, and it comes from the first IP address here. If we check the corresponding device, we are also able to see its corresponding GIT or address. That's effectively the IP address here encoded in hex. So this is what it looks like on the host. Let's do a quick check on the other pod. Then I'm going to show you how RoCE works across these 2 pods by using the host interface directly. All right, it's the same thing for the other pod. And I'm going to do a quick RDMA write bandwidth sample. So now we are leveraging the host RoCE interfaces across pods to write tons of data. And as you can see, it's close to 400 gigabits bandwidth, and it's working just fine. But like I mentioned, our workload really needs to run RoCE from their own networking namespace, because we need the security, we need the policy enforcement, we need the isolation, etc. Right? Now let's take a look at the real RoCE interface workload pods. So this is another engine. It has preview, it has default, and we depend on RoCE to share states across the preview and decode replica. And let's take a look at their pod status. Because we are leveraging models, if you look at the pod and just check this network status summary, you should be able to see the corresponding information or metadata reported by models. We have the first interface, ETH0, of course, for the front-end networking. But besides that, we have 8 additional RDMA interfaces for this pod, and they have the corresponding IP. What's interesting is this IP is different from the previous one, but it's also from the same RDMA subnet. It's the same thing for the other pod. Remember, we moved the host RoCE interface, in this case, directly into the pods. Okay. Let's check what it looks like from the, within the pod in terms of GITs and other metadata. This aligns with what we saw before. We have 8 networking devices. They have their corresponding IPs assigned. And if we check the GIT for this RDMA device, they actually have the corresponding IP reflected in GIT, meaning when workload runs from pod's networking namespace, they can check or query this GIT table, use it to do RDMA. Let's quickly check the other pod. It's pretty much the same thing. So let's move on to do a quick sanity check for RDMA. So this is to show you on the host, actually, we can still see these devices because they match to the physical device. But we no longer see those networking interfaces, right? So there's only these 2 for the front-end networking because we moved them from host to pods. And if you check the GIT table, what's interesting is there's nothing because there's simply no networking interface. This means from the host, you are no longer able to do RDMA. It's the same thing on the other host. So let's do a quick check from pod to see if RDMA works. Okay, it's the same thing for the pods. We see the networking namespace interfaces. We see the front-end NIC. And now I'm going to do a RDMA ping from pod to leverage this RDMA interfaces within the pod. Cool. We see data from between two pods, and so that's it. That's pretty much it. With this, I'm going to hand it over to John to talk about MIG and MX.
Perfect. Yeah. RoCE working is pretty cool. I think it was pretty complicated to get that to work, so this is a sweet demo. But now I'm going to show what it took to get NVLink to work effectively in the same way, and show it with hopefully a running live ChatGPT engine. So I recorded this here, so bear with me. So essentially what I'm going to do first is a ChatGPT engine is the smallest unit of an engine, or a smallest unit of compute in serving ChatGPT. So at the end of the day, an engine is a set of Kubernetes pods, and that's what I'm showing here now. We have updated our scheduling logic to be able to target these pods onto a specific rack of GPUs. So physically, these pods, even though they're virtual in the cloud pods, they are targeting a set of nodes that I'm showing here. And all of these nodes, as you can see how they're named, are in the exact same rack. So this is, if you see 0003, 0005, that is the block and sub-block in GCP that these pods are actually falling on. And so that's important because physically only those 18 nodes are connected with NVLink. So I'm going to SSH onto one of these nodes and show you the IMEX configuration that we have deployed automatically to these nodes from MIGs. So I'm on this node now, C298, 003, 005, and this is the nodes configuration of IMEX. Which essentially says, hey IMEX, here are your peers that are also in the rack. And these are the references to the other nodes in the rack. And as you can see, these host names are resolvable to the IP addresses of the other nodes in the rack. And as you can see then, with IMEX properly up, this is the fully connected NVLink domain on a given node. And the engine pods that are scheduled on top of that node are using this fabric in order to share weights and serve ChatGPT efficiently. And that's how we're leveraging GPUs, or GB200s rather, from GCP to serve engines on ChatGPT. Yeah, so super sweet project to get to work on. It was a lot of fun. I think that's it. And so yeah, oh, yeah, I forgot. Yeah, so okay, that same rack of GPUs I just showed you is actually just a MIG in GCP's UI. So this is our list of MIGs in this one cluster. So as you can see, there's many, because there's many racks here. If we click into one, this MIG has the reference to the instance configuration or the instance template that I was referring to earlier, and has all 18 nodes up and healthy in this rack of GPUs. So this is explicitly targeting one of the sub-blocks that GCP has in this physical cluster. And all of that tied together makes ChatGPT able to be served on these GB200s. But yeah, switching back to the slides, we can have Ishan come back up here and we'll intro the next sessions. But yeah, this is a really fun collaboration with GCP to work with and enabling ChatGPT on GCP.
Yeah, let's give a round of applause. So just a little bit here. So John is going to be presenting later on. There's a session this afternoon, so definitely attend that, because that will go more into the details of what was sort of introduced here. So, so please make sure. And to learn more about other sessions, here's a list. Please attend these, and these would be great to learn more about the AI infrastructure that we have on Google Cloud, including how you can use it with GKE. And as you work with AI workloads on GKE, to learn more about it, scan this QR code. It gets you to our documentation, and that lets you get started with AI workloads on GKE.
Judging by our timer here, it looks like we have 5 minutes left for questions, but we'll also be hanging around afterwards if you guys have anything we can answer.
So any questions? Yes, I think we have a mic here as well.
Thank you so much for the session. I'm wondering if you have considered TPU at all, or just curious whether, like, when you evaluated, different options, like, what are some of your decision points going with GPU, or I don't know if you're using TPU, so I was just wondering about your thought process.
You want to take that, or you want me to?
Sure, go ahead.
Yeah. We don't currently use TPUs today. It's all of our infrastructure is on GPUs. I don't think there's any reason we couldn't in the future. I think it's, again, going back to the original point of providing a unified infrastructure to our application users. It's the simplest way we want to proceed because we're moving really, really fast. Obviously, in the future, compute is compute, and we want to be able to support anything.
Just one more question on the NVL 72. I was curious whether that 72 was enough for the single rack, whether there has been any cases where you need more GPU in the single rack.
So essentially, there's 3 layers of compute that go on. There's within a single node, within a single rack, and then within a single cluster. So if you need workload that goes beyond the compute of a single rack, the way to do that right now is via the RoCE stuff that my colleague here has showed you. So that is also very high bandwidth communication via RDMA, which is remote direct memory access. So node 1 can access node 2's memory. NVLink, the fabric, is a bit an order of magnitude faster, but RDMA is also very, very fast and enables cluster-wide workloads, like large-scale training.
Got it. Like RDMA was enough for the large training across racks, I guess. Okay.
Large-scale training uses both, yes.
Got it. Thank you.
And with RDMA, just to expand on that, on Google Cloud, you can go with ML block rail groups that continue to expand, so you get a lot more capacity. Yeah, next question.
Hi, I'm wondering, for your multi-node inferencing or multi-pod inferencing, do you use leader worker set from Kubernetes? If not, have you ever considered that? The leader worker set for multi-pod or multi-node inferencing?
I'm not familiar, but I'll have to take a look.
Imagine we must have something similar internally, because for scheduling layer, we actually have our own internal primitives. But we also are looking very actively into what open source or upstream is doing. So definitely interested to hear more about it.
Okay, thank you.
Hey, I was wondering if you already moved to DRA, and have you been able to express complex topology requirements using labels? Because I saw that you've been pinning using labels. That must be pretty static at this stage. So have you run into any issues with that? And what's the plan to move to DRA?
This is a great question.
Great question.
Yeah, this is a great question. So when this was started, actually, it predates DRA, right? That's before the API has reached the maturity in upstream. So we were racing against clock, remember? That's why we kind of went our way and did our own approach in a provider-specific style. But that is, everything is evolving, and last time I checked DRA, I'm pretty happy with the current status it is. So like I said before, we are very actively looking into what open source and upstream is doing and trying to converge whenever that is possible.
I have a question, thank you. So the question regarding using the NVL72, so when you work on this platform, do you see a case that you do the 72 partition on the NVLink? So you need to do a partition on the switch side, and also you need to manage the MX, right? That's going to be 2 MX domains. So I want to know the workflow, the procedure, who controls the switch side partition, who does the MX, the configuration change, OpenAI or Google platform? Also
a great question. Yeah, so once the node is booted for us, we fully control IMEX, right? But we are fortunate that all of the GPUs that we run are single tenant, so to speak. Like OpenAI is using all the GPUs. We're not redistributing them in certain cases. So for our use case, it makes most sense for the IMEX domain to be spanning the entire NVLink domain. So we statically configure the IMEX domain today. In the future, we could use this gentleman's previous question, the DRA stuff, to dynamically configure IMEX potentially. But for now, it doesn't make sense to us to shrink the NVLink domain, since the workloads are all isolating themselves. No, we use the full NVLink domain. One IMEX, yes.
Yeah, I think one NVLink domain, one IMEX.
Yeah, and that's also tricky since these are cloud resources. So the instances come up and down all the time, right? So instance coming back, we want to minimize the ability to the forcing reconfiguration of IMEX, and that's exactly what I'll talk about in the next session. So if you're available there, we can chat way more about that. We partition a layer higher. We partitioned the workload a layer higher. So the workload itself is its own partition.
I think we have time for one more question.
Yeah, I have a question here. So what does maintenance look like with this setup? Is it whole rack, or does it go node-wise? How does it work?
Also a great question. So yeah, the whole shift of the paradigm from single node to rack-aware systems has changed a lot of layers of the stack, from scheduling to provisioning, and also including this maintenance workload. So we're actively working to build rack-aware maintenance systems, but the MIGs kind of give us the APIs through which to do that. So both we can trigger maintenance on an individual node and trigger maintenance on an individual rack, depending on the use case. But software is still being built in this space every day.
Usually what we're seeing, just for adding from a Google Cloud perspective and what most customers are doing in best practices, we're thinking more and more of maintenance at the rack scale, and so that customers or users are not having SKUs within a rack, and that applies to sort of firmware updates and the compute maintenance, but also when you're running with Kubernetes, you want to kind of make sure that that's also consistent there. So that's kind of how we're thinking, moving from a node basis over to, in GKE terms, node pool or sub-block or the entire rack. Yeah.
And the last bit to add to this question is, at workload level, we do have abstractions, so we are more tolerant to individual node failures at rack level, if that makes sense.
I think that's all the time we have. We will be hanging out here on the side, so if you have any other questions, please come up. Thank you so much for joining us, and a big round of applause for John.
Thank you.